Hi, everybody. This talk will be a little bit different than most that you've probably seen today, and that also you'll see throughout the week at CoRL. My background is in computer vision and machine learning, and today I'm going to be talking about ways in which we can create vision systems that are more reusable and reliable. I'm going to explicitly focus on two different recent works out of our lab in this space, and maybe speculate, especially during the panel session just after this, about connections to the robotics space. So of course, in robotics applications, many of you are using perception as an input. It can be very helpful for understanding your environment, for making decisions, but oftentimes you don't necessarily have access to all of the data that you need, at least in situ, in kind of the domain that you're working with, in order to be able to extract the salient information. So today's talk is going to be focusing on that. How can we come up with different mechanisms for, first off, understanding how we might be able to generalize vision systems out of the box. Hopefully you don't even need to collect lots and lots of data in your own environments in order to get them to adapt to your setting. And then also, how do we better understand conditions under which they might fail? So first off, to get us started, we can begin by just thinking about, you're pointing at the screen. No, okay. We can begin by just thinking about what are ways in which, actually, this is just for the people in the room. Let me see if I can figure out how to move my mouse over here and get this. Ugh. It may or may not work. It is very challenging to get my mouse. There we go. Which way do I need to pull it? All right, there we go. Good. All right, cool. Left blocked. People online don't notice what happened. All right, so here's what we want. Here's the idea. We're talking to people where they might have kids. They might have interacted with kids. And oftentimes what you see is a possibility is that what they can do is they can teach their kids about a concept, maybe in a domain that's completely different in visual appearance to the real world. So for example, they might be reading them a kid's book. And in that children's book, there's a cartoon version of an elephant. They can do this, they can read about the elephant, and then what they can do is they can take their child to the zoo. And once they've gone to the zoo, they'll see this elephant and be able to recognize it. And those of you who have kids know that this is in fact a capability that young kids have the ability to do. So naturally, we would assume that a computer vision system should be able to do a similar sort of task. Of course, those of us who have used these systems know that that capability is easier said than done. Okay, so fine. Maybe this is too big of a gap to assume out of the box, but at least if we've seen an elephant in the zoo with an image like this, we'd hope that we'd be able to recognize the elephant in a new context, like if we saw them on safari. Or if we've seen them on safari, hopefully, if they start walking towards us in fog, we can still continue to recognize them. So these seem like capabilities that we should be able to have, but unfortunately, these have strikingly different visual appearances. And as a result, our systems that we train on data that looks like one of these settings may fail to generalize in a new setting. So in order to have a reliable vision system, the goal that we want is we would like to be able to have vision systems that can perform tasks like understanding what is in a scene in the way that you would expect, but at deployment time. So not just in a closed world environment on the data that we've collected, but really under all the conditions that we would like to be able to use this system in. And this is where it becomes most important, especially for robotics applications, because oftentimes you're not the one necessarily that's the core developer of these systems. You want to be a user of them. So for today's talk, I'm going to focus on two key aspects in this space. One of them is on robust training. How can we potentially propose a mechanism for being able to get these systems to work out of the box in as many contexts as possible? And the other one is going to be on robust analysis. And I'll explain more what that means later. But really, the idea is that your system is never going to be working perfectly under all conditions, but we want to be able to understand upfront what are the conditions under which it should continue to work. That will be able to help us to know when we can keep relying on it. Okay, so let's get started with the robust training. Now, in any visual setting, especially a visual setting that relates to embodied tasks or tasks that are kind of operating over time out in the real world, we know that our data is subject to change. So one sort of example application area that my lab works on a lot is that of self-driving.
we have these dash cam footages, we drive around different environments. Of course, that environment changes all the time. We might have different times of day, we might have rain, we might have going through different structural settings like through tunnels, and you might be in an urban environment, you might have pedestrians, so on. Kind of a list of things that can change goes on and on and on. So in the classical computer vision supervised learning setup, in order to be able to solve such a task, what we would do is we would collect paired examples of images like the one on the left and annotations like the one on the right. In the case of trying to be able to solve a task that requires you to understand something that has to do with the spatial layout, maybe we would collect pixel level annotations like the one on the right. But when we talk about all of this sort of variation that you might encounter, it becomes intractable, first off, to even have captured all of the possible variations that you might see at test time. But even if you did capture a large percentage of them, annotating in this particular mechanism is prohibitively expensive. So even the companies that are trying to do this as a commercial output have to expend very, very large budgets to be able to get sufficient data to have a capable system, acknowledging that it is still not covering all of the types of variations that you might see at test time. So instead of relying solely on these kind of drive around, collect the data, and annotate it in this cumbersome way, of course, there's a big part of the population, both in the computer vision community for applications such as this, also in the robotics community, that is trying instead to take an approach of learning and simulation. You know, it's obvious why this would be of value. If we're able to learn in simulation, it's a lot cheaper, it's a lot faster, especially when you think of the robotics application, where sometimes data collection itself can be very, very slow and cumbersome, and maybe restricted to very few lab settings. So the idea of being able to learn in simulation is pretty great. If we could do this, we could really reduce a lot of the issues that we're encountering. We could generate lots and lots of forms of diversity. The problem is that there's a gap between the appearance of our simulators and the appearance of our real world. And what results in response to that gap is that models that we train to solve vision tasks on our generated images, they might appear to work really, really well when evaluated within our simulator setting, but they are working less well when deployed into various real environments. So this sim to real gap is something that we can see under many different settings. I'll show you one example here. So this is the setting of training on images taken from the Grand Theft Auto game, and then trying to evaluate them on images taken from the Cityscapes driving data set. This is a data set, just a dash cam footages taken around German cities. Okay, so here's one real image. The desired output would be something like this. This is the ground truth. But if we take a model that was trained in simulation and just try to apply it to this image, you get an output that looks like this. That's not so important, all the mistakes that it's making. The only high level importance is that there's a lot of mistakes, and there are mistakes even on things that should be quite simple, like the road. So this is disconcerting, and it clearly means that you can't use it out of the box. So we need to be able to do something to be able to close this gap a little bit before we can start to use these systems. So the first work that I'm going to talk about today is one that was just presented a month ago at the ICCV conference. This work is called PASTA. It is a data augmentation technique. So probably many of you are familiar with this type of strategy for closing the sim-to-real graph, which is that of essentially, I think domain randomization is one of the ones that's quite popular in this community, and for good reason. Basically, what we've seen over and over again is there are learning interventions that can work quite well for closing this gap, but one of the first things that you can do to close it right off the bat is basically to add more variability to that training data. So overall, the problem statement that we're addressing in this work is that of sim to real. We're going to focus heavily on this driving setting and semantic segmentation, which is labeling all of those pixels, but it can be used for a variety of different tasks as well. We have some extensions in the paper if you're interested. Overall, our goal in developing this work was to be able to create an algorithm that was as simple to use as possible. It can be used in conjunction with more complicated learning-based solutions, but for this work, we wanted just a plug and play, kind of something that would modify the data itself. That means that it's architecture agnostic as well. Okay, so broadly, as I keep mentioning, there are kind of two big spaces of ways in which people try to close this sim to real gap. One of them is learning-based solutions, or rather changing kind of the objective function in order to add invariance or to add robustness to the learning system. And on the other end of the spectrum, there's changes to the data. And these changes to the data are usually trying to inject extra forms of variability to that training data such that you're less likely to overfit to it. PASTA is in the data augmentation camp. So one of the things that we did when designing this particular approach was we started out by thinking deeply about what is the difference between the simulated and the real data. So there are a lot of different subtle differences. We can kind of group them roughly into two types of settings. We have low-level statistical changes, things like changes in brightness and contrast, and we have perhaps higher-level changes getting closer to patterns, textures, and also just raw content, like they could have different cars in the different scenes or different scene layout. But one of the striking things, even at the lower-level statistics, is that there is quite a big difference in terms of the variability in the Fourier space of the simulated data and the real data. And why this is important is because, again, when we're training on the simulated data, the model is very good at overfitting to the types of low-level statistics in that original data. So one of the ideas that we had here, and I'll explain it in more detail in a second, is that if we could create an augmentation scheme that would make our simulated data have statistics, low-level statistics that were more similar to the real world, perhaps we would be less susceptible to overfitting at training time. So this was inspired by some early works that have looked at kind of, I won't go into this in too much detail, but have looked at some of the distribution overall of images in terms of the frequency spectrum that's available. And you can roughly think about breaking down the frequency spectrum into 3 different buckets, low, medium, and high frequencies. And the reason why we might do that is because quite frequently the lower frequencies might control things that have to do with the overall image, and the high frequencies might control things that have to do with kind of like subtle perturbations that maybe not even human perceptible in many cases. Okay, so one of the findings that we had just doing an empirical study looking at a bunch of different real data sets and simulated data sets was, again, that there is substantially less variance in the simulated data than in the real data. And not only is there less variance, but when you consider these high frequency components, that gap expands, meaning that there is even more variance in the high frequencies compared to the high frequencies in the simulated data. Okay, so that sets us up to start to describe the PASTA algorithm. We have this intuition, we've noticed this empirical observation that there's this big gap. There's a lot more variability in the high frequency spectrum all throughout, but especially the high frequencies in the simulated data. So now what we're going to do is we're going to seek to correct that. And again, the goal here is not to create a more realistic image, it's to create an image or a set of images that have statistics that in the high frequencies and all frequencies that are more akin to what you would see in the real world. So we're going to start with our simulated image. And then what we're going to do is we're going to take an FFT, we're going to get the amplitude and the phase spectrum. Now, there have been prior work that have shown that the amplitude spectrum controls things that have to do with the style of the image, and the phase controls things that have to do with the content. We don't want to modify the content, so we're going to keep that one fixed. We're going to focus our efforts on augmenting the amplitude. And we're going to augment it in a particular fashion that essentially focuses more on making sure that we have higher perturbation at those higher frequency spectrums. I'm going to skip over this. This is just if you're interested. We have a particular way, a particular structure to adding this perturbation. The only really important thing is just that we are adding more perturbation as you get into the higher parts of the frequency spectrum. That's, again, based off of our empirical observation. So once we sample the types of perturbations that we would want that vary with the amount of frequency, then we can essentially augment our original amplitude image and combine that together with our unmodified phase image. So we haven't changed the content. do an inverse FFT and get our augmented image. Okay, so this is the whole procedure. It's quite fast, it's quite simple, it's something you add in your data loader, it's not going to modify your architecture in any way. The output images, as I mentioned, do not look more realistic. So that's important. This is a different type of strategy. It is not trying to make them more realistic, but if you were to compute the statistics of the frequencies, it is closer, closer to what you would see in the real world. So it remains to be seen, how well does this work? Well, we tried it on a bunch of different tasks for the semantic segmentation setting. The first item here is a baseline. This is for that Grand Theft Auto as our simulated data, and the real data here are 3 different real world data sets: cityscapes, BDD, map layer. They're taken from different parts of the world, different cameras, different cars, and so on. The number that's shown here is a summary statistic. So we basically took the same one model that was trained on the GTA simulated data, and then just out of the box, without looking at any of the other data, just out of the box, evaluated and averaged the result. So this first number here is the baseline, so if you don't do anything. And then this last number that's being shown is what happens if all you did was you perform this past augmentation before you trained your initial model. So you get a pretty sizable performance improvement at this evaluation. You can compare this to other approaches or even combine it with other approaches. This particular approach here, it was taking more of a learning-based approach. So any learning-based approach could be used in conjunction with this data augmentation approach. Here's another setting where we look more specifically, a different architecture segment former. On the previous page, it was a CNN-based architecture. As I mentioned before, it's a data augmentation, so it's architecture agnostic. The takeaway here is just essentially that across different settings, different architectures, different data sets is kind of working out of the box pretty well. This is a different task, object detection, where we go from 39 to 56. And you can combine it with other data augmentation schemes to get even further improvement. There's probably a cap, there's probably diminishing returns to how much augmentation you can do. And just for reference, for those of you who are familiar with a domain adaptation setting where you look at target data and make modifications to your model in response to each specific new deployment setting, what we found was that this method was actually outperforming those approaches, which told us that this gave us a better out-of-the-box performance than even the ones that would be using some of the deployment data. All right, so altogether, this method, and sorry, I know I'm going pretty fast here, just kind of get through stuff, but altogether, this is a plug and play method. It's basically data augmentation, and it is inspired based off of empirical observations of the statistical differences between the real and simulated data. All right, up next, I want to talk about robust analysis. So the previous work was just saying, hey, we need to work in the space of developing algorithms to be able to have vision systems that can work out of the box more effectively. But they're never going to be working perfectly in all settings. And one of the worst things that could happen is if we assume it's going to work well, we deploy it and it fails. So one thing that we have started to look into is we've started to try to understand whether or not there's a different way that we can evaluate existing models. And for this, I'm going to talk about this work that's going to appear at NeurIPS in a month called Lance. And the idea here is that we'd like to create essentially dynamic test sets. So the standard protocol in machine learning is to hold out, usually in an IID way, hold out part of your data and evaluate it in order to benchmark performance of a model over time. But again, we go to any real world setting and we know that the type of data that we'll see over time actually changes quite a lot. And so it can be a little bit misleading to just have one static test set that we benchmark performance of models in. It's missing out on quite a lot of the data that we'll actually see later on. And let me give you an example of ways in which a model can appear to have very high performance on a static test set, even if not necessarily for the right reason. So this is one image taken from the ImageNet test set. The ground truth label for this image is dog sled. And actually, an off-the-shelf model, in this case, the ResNet 50 model, is able to correctly predict dog sled here. But if you stare at this image hard, you may notice that actually there's no dog sled that's visible in this image. So this is a funny case where the model has learned to pick up on some subtle correlations in the data. Maybe it's the type of dog, maybe it's the fact that they have a little bit of a harness, maybe it's the snow. We don't actually know what it is necessarily out of the box. All we know is that we measured accuracy and the model did well at predicting dog sled. So you might deploy this and say, okay, this model is really, really good at predicting dog sled. And then it may fail at some point. It may not predict a dog sled. And you don't know why. What correlation that was there before is missing now. So this is where we are trying to be able to design a system that can probe these models and figure out beforehand what are the correlations that they are leveraging in order to make these decisions. Or conversely, what are the conditions, the changes under which they would begin to fail. So this is where our method Lance comes in. We are going to try to generate counterfactual images that can help us to identify conditions under which the model will fail. So for example, with this particular image, one thing that we could do is we could change the breed of dog. So in this case, we changed the breed of dog from Husky to a Golden Retriever. And what we find is that we're still predicting dog sled. We could change it from a Golden Retriever to a Labradoodle. We're no longer predicting dog sled, or even a Pomeranian. Okay, so that what this is telling us is that perhaps there is some sensitivity under these conditions or some correlation between dog breed and prediction of dog sled. So how can we do this? How can we get to the point that we have these counterfactual images? And again, our goal overall is to take an off-the-shelf model that we already can evaluate on a static test set, and we would like to be able to evaluate it on these dynamic test sets. So because we already have this model and we already have a test set, of course, for any test image that we have access to, we can pass it through the model and get out a prediction. In this case, it's a correct prediction. It's predicting howler monkey. We'd like to understand the conditions under which it will stop predicting howler monkey or change its predictions more broadly. So the first thing that we're going to do is we're going to use an off-the-shelf captioner to generate a descriptive caption for this image. In this case, we generated a black monkey sitting on a tree, on top of a tree with green leaves. Now, the intuition of what we're going to do is rather than making interventions or perturbations directly to the image space, we're going to use language as a medium to help us to be able to create controlled variation. So in order to do that, we're going to take this caption, and our goal is to train a small language model. Basically, we did low shot fine tuning on an off-the-shelf language model to be able to teach it how to instruction follow. The instructions that we want it to follow are to be able to modify this caption in a way that does not change the meaning of the image. So for example, we would change it to be able to say orange leaves instead of green leaves. We can then use it with, again, a frozen, we're not training anything here, off-the-shelf image editing model that's going to take as input both the original image as a constraint, as well as our new caption, and generate this new image. So in this case, our caption was changed from green leaves to orange leaves, and our output image should look almost the same as the original, but just with orange leaves. Now we have a new image with which a new test image that we can place into the model, and we can evaluate the performance. In this case, the model's performance changed to predicting gorilla with high confidence, which is incorrect. And so we can perform all these perturbations systematically and randomly. We can automatically generate lots and lots of these perturbations. And at the end of the day, we can programmatically surface the ones that resulted in the most output variation. That can help us to be able to identify what are the perturbations that the model is most sensitive to for a particular class. In order to add structure to this process, I'll skip over the details, but just to tell you very, very briefly, and I'll show you some examples that'll make it more clear, is that we taught the language model, or we asked it to instruction follow to modify only 5 types of things: subject, object, adjective, domain, and background. And I'll show you an example. So here's an example of a subject edit. This is the example I showed you before. So this is making a change to the dog breed. It's important that you are not changing the ground truth class. So the ground truth class here was dog sled. We don't want to change anything to do with that. But what we can change is some other subject, like the dog breed. And then again, we can look at the output predictions, how they might change. Here's an example of an object edit. So these are, again, a howler monkey, and the modification here has been from changing from a forest to a bamboo forest, and this resulted in very minimal change. This is not something the model was as sensitive to. Here's a background edit where it went from a playground to a snowy playground. Interestingly, not only did the correct predicted class of horizontal bar become lower, but you start predicting or hallucinating classes like ski and pole. So you can find persistent correlations in the model in a couple of different ways. And here's the last one I'll show, which is domain edit. Here we're changing it from a photo of this particular type of monkey to a sculpture. Again, all of these are not predefined. These are being sampled from the language model, so we can generate lots and lots of them, and then we can surface the ones that affected the most change to manually look at. I think in the interest of time, I'm going to skip the numbers just because they're less interesting than the pictures, and just end by showing you an example of that. We can do this not only for a single image at a time, but we can start to surface class level systematic mispredictions. So what we can do is for the same class, we can take a bunch of test images. This is the howler monkey class. We can take a bunch of different test images and perform the same type of perturbation across them in order to surface whether or not there is a consistent variability in response to one type of perturbation. So in this case, the change of the intervention is changing color. So changing the leaves in the first case to be the orange leaves resulted in some amount of change here in the output prediction. We change a green field to be a pink field. The model did not correctly predict originally, but now correctly predicts. And in the last case, we add snowy leaves. That didn't result in a substantial change. So this is just an example to highlight that you can use this tool to be able to evaluate more systematically across a collection of data rather than in a single data, to be able to come up with what are the most sensitive attributes of the model overall. All right. With that, I will conclude by just saying that today's talk, as I mentioned at the beginning, it's a little different. I wasn't talking about robotics directly, but talking about vision systems and how we might be able to make them more reliable overall. First, by talking about closing the sim to real gap or better generalizing out of the box when we train in simulation using a new data augmentation algorithm. And the second is promoting this idea of dynamic test sets so that we can understand where or under what conditions a model might fail, even if we don't yet have access to the data to evaluate them. I want to thank all of my lab members who I tried to highlight for the various parts of the work, but many others contributed to this work as well, and take any questions you might have.
Yeah, thank you so much. It's a great talk. So for the lands part of the presentation, I'm curious, after you find the large delta in the performance of the model, what techniques do you use to try and get the model to perform correctly? Manual tuning, or you reference the first pasta, approach?
Oh, that's a good question. So the Lance is an auditing tool. It's not necessarily yet a mitigation tool. So I think what you're asking about is how could you use that information to better improve the model. So one thing it kind of depends on your scenario and your application. In some cases, you could take an invariance approach if what you surface is you decide that this is not something you want the model to be picking up on or caring about. Then there are various different regularizers you could add. Not saying we've done this yet, but that's one thing you could do. If what you decide though is that, oh, this is actually an important correlation that's just underrepresented, you could even take an approach if you have the capability of additional data collection.
On the pasta portion of the talk, so first observation was that sometimes it seemed like the Grand Theft Auto or GTA 5 photos were almost a more realistic color spectrum than some of these camera images from the cityscape data set that are
Yeah.
just so dark.
Yeah.
So I was curious, what happens if you go kind of the other direction? Or did you think about going from cityscapes to GTA 5 instead of?
We, not for that work, we didn't try it. I will say also that I showed a lot of examples from CityScapes, but we also use the same model on Mapillary and BDD, which don't have that same problem. BDD is actually like anytime I showed a video of the driving scenes, that was BDD, so they look more normal lighting. I have no idea why Cityscapes looks so gray. It's very strange. Yeah, in general, if you wanted to go real to sim, I think you would need to design a different augmentation. Ours is not, it's not a learned augmentation in the sense that we kind of measured the difference in the statistics and then crafted a perturbation scheme based off of that. So if you wanted to go the other direction, you have to do that procedure again.
All right, maybe we can take one final question.
I had another question related to hypothesis. So I think the idea of like matching the statistics is really really cool. I'm curious. So I think the way that you proposed was to kind of add back in the high frequency components that weren't present. At least that was the trend. And I can imagine another way to do this would be to kind of artificially take them away at the test time, like basically like blurring an image.
Yeah.
So I'm curious if you tried that, essentially taking away information that might be fooling the model and seeing if it compares to that or how things compare to that.
That's an interesting idea. We didn't try that, but the closest thing we have tried is that we have tried evaluating on lower resolution images, which is sort of like the blurring idea. And it usually has worse performance, though I don't think it has anything to do with sim to real gap. I think it's just you have less details to make the predictive decisions with. So there might be something more sophisticated than just resizing that you could do, but we haven't done it yet.
All right, let's thank Judy again.